Okay, let's get started, please. So today we're going to be talking about the fundamental theorem of calculus. So, by the name, you can tell it's very important. I once had lunch with my postdoc advisor, and out of nowhere, he asked me, he said, so, if you could plagiarize one result in all of mathematics, what result would you plagiarize? What result would you put your name on, to say that this is your result, even though it's not actually a result? And I said, I thought about it for a while, and I said, the Calderone Zigmund decomposition. Because in the field of mathematics that he's in and that I'm in, this is like the ultimate tool. Like all the great questions. There are all these questions, and it turned out that many of them could be attacked and resolved using this tool called the Calderone Zigmund decomposition. And he said, "You are thinking too small. I would go for the fundamental theorem of calculus." And I was like, "Oh yeah, yeah, you're right. It should be the fundamental theorem of calculus." Yeah, because okay. Okay, so we've already said something called we've already introduced something called the fundamental theorem of calculus, but that, like I said, that was really part two. Here's what's called the fundamental theorem of calculus, part one. Okay, so let f be a continuous function. So f be continuous on some closed interval AB. Okay, and then let me say it this way: say f is continuous on AB. Okay, suppose you have some continuous function. Okay. Then you create a function. Let f, capital F, be this guy. You create a function, and the way you do it is you say, I'm going to take the definite integral from of the first function from a to x. Okay. So the picture you want to have in your mind here is like this. You have your first function. Okay. So this is f. Okay. And then capital F is going to be if I want capital F of x, then I take the integral of the original function from a to x. Okay, so capital F is going to be this integral. And maybe it's sort of, I'm going to draw f. I'm going to draw little f as if it's positive, just to make it easier to visualize. Okay. So here's little f, right? And if I choose some number x, then capital F is going to be the integral from a to x. Capital F of x is going to be the integral from a to x. Okay? Yeah?
So capital F is no longer representing the antiderivative?
Right. So capital F is just this function here. Okay, we're not using it. So previously we always used this capital F as an antiderivative. Right now I'm just saying that this is this area. Okay, so this is you think of this thing as some sort of area function. Okay, so for example, if I say capital F of A, what's the value of capital F at A? Everybody write down something. What's the value? What's capital F at A? Okay. Nico, what is it? Well, it will be the area from A to A of little f. What's the right? It'll be the integral from A to A of little f. Oh, what's that?
Wait, so capital F is the integral
of little f
of
from a to whatever. In this case, the endpoint is the second endpoint is 0. So what's that? Anybody? 0, right? That's just 0, right? Because it's the integral from a to a. Well, if you're integrating at a point, you just get nothing. Okay. And then what would be f of b? Well, that's going to be the integral from a to b of f. Right, so that would just be the whole integral from a to b, the whole definite integral from a to b. Okay. Everybody getting a sense of what this capital F guy is? Right, it's the integral, the definite integral from a to some point. Okay, so it's just it just takes part of the integral, whatever your x is, it's going to integrate from here to there. Okay, so you start off with your function and you create this area guy, right? And then it turns out that f, this capital F guy, is a differentiable function. On a comma b. And the derivative of it is little f. Okay, so it actually is an antiderivative. Okay, I was fooling you. Yeah. Okay. So this area guy, this area function. Right, so the point is that this area function is an antiderivative. F is an antiderivative of little f. Okay. So if you have some continuous function and you create this thing, then you've created an this thing is actually an antiderivative of the original guy. Okay. So to be kind of silly about it, if I have a function like this, e to the x squared, and I say, find me an antiderivative of e to the x squared, can you come up with an antiderivative? Let me say this. Can you find an antiderivative of e to the x? Sure, what? E to the x, right? Easy. What about e to the x squared? Can you find a function whose derivative is e to the x squared? 1/3 e to the x to the 3. Let's think about that. When you differentiate it, what do you get?
I regret it. Never mind.
You regret it. Right? You're gonna use the chain rule, right? So let's just look at the derivative of e, right? By the chain, you're gonna get e to the x. What's just for practice? What's the derivative? Somebody? Anybody? By the chain rule, right? You got e to some function. When you differentiate it, you're going to get e to that function times the derivative of that function, right? So you're going to e to the x3 times 3x squared, right? Times 3x squared. Okay. So not a bad idea, but it won't work. But actually, this is a trick question because there's no function. There's no function that neatly. That you can write down neatly that is the antiderivative, except when you play something like this. Okay, so you can make an antiderivative. We could make one if you wanted an antiderivative of e to the x squared. Well, you could make one. You could say here's the function. Take the integral from say 0 to x t squared dt. Then if you differentiate this guy with respect to x, you're going to get the integrand evaluated at x. Okay, that's what this is saying here, right? If you start off with a function and then create this area guy, then the derivative with respect to x is going to be the integrand evaluated at x. Okay. this is an antiderivative. This thing here is an antiderivative of e to the x squared. Okay, we'll do more of that in a second, but first let's think about why it happens. Okay, so what we're saying is that this thing here is an antiderivative. Okay, so let's think about it. Why? Right. So let's consider f prime of x. Right. Okay. So this is going to go back all all the way to the previous chapter. What's the derivative of a function? Well, it's going to be the limit of what?
H is 0.
As h goes to 0 of
F is minus 8.
f nope.
X minus H.
Nope, close. X plus h.
Minus.
Over h, right? Or, I mean, like x plus h minus x, right? Which is h. Right? You all can pretend to know this, to have remembered this. Okay. Right. That's the definition of the derivative. Remember? Okay. So let's look at it. Right. So let's just think. What is that? The limit as h goes to 0. F of x plus h. Right. So that's the integral from a to x plus h of f. Right. This guy. That's his first term here. Okay. Capital F of x plus h is the integral of little f from a to x plus h. Right. And I'm going to write over here. This is going to be capital F of x, which is what?
From A to X.
From a to x. Right. And to be proper, maybe I should put in some, some variables here, but you know what I mean when I just write, the integral of f. Okay.
What does it say in the first integral? F t.
I'm just gonna write f.
Oh.
Okay. And so when I write that, it just means the integral, with respect to some variable, whatever variable you like. But don't use x because we've already used x. Okay, and the whole thing divided by h. Okay. Okay, I'll give you 30 seconds to think of something to say about this. Make some observation about it. Okay, like you can simplify this a little bit. Or what can you say about the numerator? No.
Can you take out f?
Can you take out f? Oh, you mean you're thinking like you can somehow factor it out or something? No. Right, because this is the integral of f. It's not a multiplication,
Okay.
and f isn't a constant. Okay, yeah. So I think what you're thinking, and that's probably because of my reckless communication. You're probably thinking that f is a constant. If f were a constant, that you could pull it up. Yeah, but f is actually a function that changes. Yeah. Sarah?
Can you say something about the integral from A to H?
From what? A to?
From A to H.
From A to H. Let's think about it. So let's see, we've got A here, we've got x here, like x plus h. Right? So we're taking somebody else had, yeah.
So x to 8.
It'll be the integral
X to 8. X plus.
x to x plus h. Great. Right? Because you've got, the first one is the integral from a to x plus h. You subtract off the integral from a to x, right? And you're left with the integral, this integral here, right? So you end up with the limit of 1 over h, the integral from over x plus h, over f. Okay. let's think about that. Right? You have this area here. Right? You've got this area. Right? You have this area, and right, that's this thing. That's the area in pink. And then you divide it by h. What does that mean? What does that mean geometrically? You have an area and you divide it by h. Well, first off, where's h on this picture? What is h? H is
The distance between x and x plus h.
yeah, h is the width of the base, right? H is the width of the base, right? So you have some area, right? You have some area, and you divide it by the width of the base. What does that give you? Kayla?
The height on the side.
The height? Well, but I mean, if it were a rectangle, yeah, right. Then this height would be right. Let's call this area A. Then the height would be A over h, right? But it's not a rectangle, right? But you're basically on it. Yeah, Sarah.
Do you get like the average height?
The average height, yeah. So what you get is the height of a rectangle with the same area, right? You get the height of a rectangle with the same area, right, as the pink area, right? Same area as the pink part, right? So you get a rectangle. Got all these colors here, great. You get a rectangle that has the same area as the pink area. Okay. In other words, it gives you the average, right? It gives you the average value of f. Right. So this thing here is notice that this thing is the average value of f on x plus h. Yeah, Sarah.
What about the limit?
Yeah. So that part, so this thing here is the average value. But we're taking the limit as h goes to 0. We're taking the limit of that as h goes to 0, right? So here is x plus h, right? We say take the average height on this. Take the average height on this box. Okay. Now let the box shrink. Right. Let h go down to 0, and what happens to those average values? What happens to those average values as h goes to 0? Don't blurt it out. Just think for half a minute. Say. Talk to somebody.
So, what happens to the average values as h gets smaller and smaller? So the distance between the students, what happens to
Okay, who would like to say? Anybody? Julia?
It gets closer and closer to x, which is like f of x, like that.
Gets closer and closer to this value, f of x. Right? F of x is it, right? Right, because the average values, right? You have the average value of the box, but the box is becoming small, right? The box is becoming thin, and you see that the average value gets closer and closer to the average height over this interval gets closer and closer to the height at x, right? The height at x, f of x. Good job. F of x. Okay, and that is the fundamental theorem calculus number 1. F prime is f of x. Julie, I'll give you a bonus point on the final. Okay. Any questions on that? Any questions on that? One of the most important theorems, mathematical results of all time, maybe. Okay. So that's the fundamental theorem of calculus. Whenever you have a function, you can make a. It's possible to create an antiderivative out of it by using this area guy. Okay. By using this area guy. Okay. I'm going to erase this part over here. Is that all right? So, okay. So connection with fundamental theorem of calculus II. Okay. Observe. Right. For this antiderivative, what's f of b minus f of a? Right. For this one that we just made, right? We just made this. We have a function. We create its antiderivative. Notice what happens if you look at the difference at the endpoints. What happens? Well, what's f of b? We said it already? It's over there? F of b is the integral from a to b of little f, right? What's f of a? The integral from a to a, which is 0, right? Okay, so you see that for this antiderivative, the difference at the endpoints is the integral of the little guy. Is the integral of the original function, right? Okay. So the way you want to think about this is pretend you forgot about the fundamental theorem of calculus II that we learned a few days ago, okay? And somebody just gives you the fundamental theorem of calculus I. You say, oh, well, look at this. This is kind of interesting. If you look at the difference of this antiderivative at the endpoints, you get the integral of the small function, of the little function. Right. Is that clear? Anyone? Okay. Now, suppose you have any other antiderivative of little f. Let's say g. Suppose somebody gives you another antiderivative. Okay, capital G. Okay. Okay, so you've got two functions. What can you say about G's relation to capital F, capital G and capital F? They're both antiderivatives of the same function. So what?
Are they equal to each other?
They're not. They're almost equal to each other. They are.
They're equal except for one constant?
They're equal except for a constant, right? So you know that G is F plus some constant by the mean value theorem. Okay. So if you look at G of B minus G of A, who sees the nice thing that happens? give a point on the bonus exam for who sees the funny thing that happens? Kayla?
Is it just the same as the one was f of b minus
You're saying the right thing, but you haven't said what the funny thing that happens.
okay.
Sarah?
Maybe it's not funny, but the C's cancel.
That's the funny
Yeah.
thing. Okay, I guess it's not that funny. Okay, the C's cancel, right?
It's a
So you
little
get
funny.
f of b, thank you. Right, so f of a plus c, right? The C's cancel, and you get f of b minus f of a, right? Which we already saw was the integral of little f, right? So what does this show you? This shows you that if you have any antiderivative, then the difference at the endpoints is the integral of the original function. Okay. So this is another way of thinking about, I think this way is sort of cleaner, a cleaner way of thinking about fundamental theorem of calculus II, right? So remember, the other way we explained it was using those numbers, and they all canceled out, and we had a telescoping series sequence and series that canceled out, and then blah blah blah, using the mean value theorem on every interval. Right? That's okay too, but I think this is nicer. Right. So this is an alternate way, right? Alternate proof of fundamental theorem of calculus II. Yeah, the very useful fundamental theorem of calculus II. Okay. Right. What you say is that if you look at the antiderivative we created, then for that guy, it's very clear that the difference at the endpoints is the integral of the original function. And then you observe that by the mean value theorem, if you have any other antiderivative, well, it's going to differ from that guy by a constant, right? And so when you look at the difference of the endpoints, you get the same difference because the constants cancel, and then you go back to the integral again. Okay, any questions? Okay. So let me step back to, so one thing that people do with the first fundamental theorem of calculus is what I was talking about earlier. That if you say, well, look, if f is this thing, then f prime is f, right? So you can differentiate these sorts of integrals, right? You can combine that. You can make that a little bit more complicated by combining that with the chain rule. Right. If I have suppose I have something like this, the integral of a to u of x of little f x u. Okay, so you're integrating from a to some function of x rather than just x. Okay, and I say I'd like you to differentiate that. What's that going to be? Yeah.
Is that a u?
That's a u. Yeah.
Thank you.
Can you see what that's going to be? Evan, yeah.
So evaluating f at e of x. Plus c.
You almost have it. You almost have it. So, okay. Let me read it like this: f of u of x, right? Where f is this thing.
Yeah. Oh,
This is f of u of x. When you differentiate f of u of x, what do you get? Go ahead, Evan.
So I have what?
When you
Oh,
differentiate
the
a composition, you're going to get f
F prime of u of x,
Mhm.
u prime.
u prime x, right? But what's f prime?
That's just that.
That's just f, little f, right? So you get f of u of x, as you said, times, by the chain rule, u prime x. Okay, so let me do an example just to make this concrete. Okay, so okay, so let's say okay, so d dx e to the t squared dt from 0 to x squared. Okay, so here's an example, right? You want to take the derivative of this integral. It's from 0 to x squared rather than from 0 to x. Okay. So do you want to try it? Maybe try it for half a minute, and then I'll say how to do it.
Is that from e to the t?
E to the t squared? Yeah. Okay, turn to somebody nearby and say, this is what you get. Okay, let's start off with an easy one. Suppose I don't have a squared here, and you differentiate this, what do you get? Suppose I don't have a squared, then what's the answer?
E to x squared.
Just e to the x squared, right? That would just be e to the x squared. Okay. Now, suppose I have a squared there. Right? Well, you need to take the derivative of the function and evaluate it at x squared, right? So that'll be the derivative is e to the x squared, so you evaluate that at x squared, right? And then multiply by
The derivative of x squared.
the derivative of x squared, which is 2x. Right? You get little f, that's the integrand evaluated at u of x, right? The integrand evaluated at u of x times the derivative of u of x. Let's do another one. Suppose I have d dx of, say, the integral from a to sine x of the square root of 1 minus t squared dt. Okay. Anybody want to say? You're going to get Kayla, go ahead.
1 minus, the square root of the quantity 1 minus sine square root x times cosine x.
Very good. Right? You get the integrand evaluated at u of x times the derivative of u of x. Right? Okay. So it's just a chain rule, right? It's just a chain rule. Right? You take the derivative, right? You take the derivative of the outside guy, right? This is the outside guy, right? And then you evaluate it, evaluate it at the inside guy times the derivative of the inside guy, which is the sine here. Okay. Right. Okay. Is any questions about that? Just one silly example. Suppose I write it like this: a over sine x, from the integral from sine x to a of the same thing. In that case, what you can do is just say, well, I'm just going to reverse it and put a negative sign on it. Remember that the integral from a to b is negative the integral from b to a, right? So I'm just going to reverse it and say this is negative the integral from a to sine x. Okay, and then you just get negative what you got the last time. So you might see this sort of thing in the homework. Okay. Okay, I'm going to stop there. I'm going to stop here today.